In this video, I will be introducing vectors and some important terminology. So first we need to differentiate between a scalar quantity and a vector quantity. A scalar quantity can be described by magnitude only. So examples would be something like temperature. It's 5 degrees outside, or a distance, you travel 5 kilometers, or the speed on the highway, you're driving 100 kilometers per hour, or a mass, like 10 kilograms. A vector, however, can be described by magnitude and direction. So we can turn speed into a vector if we add direction, and then it's called velocity. For example, you're driving 80 kilometers per hour in the west direction, or a force of 10 newtons being applied downwards. Another example would be weight, and that includes having your mass being affected by gravity that's pulling you down. Now, some notation. A vector can be represented with arrows. So for example, this is a vector. The start of the vector right here is called the tail. Here's the tail of my vector. And the end is called the head. So where the arrow is the head of the vector. Now, we can represent the vector using the endpoints of this line segment or this arrow. So for example, if the arrow starts at A and ends at B, we can represent this vector as vector AB with the little arrow on top. Or I can use a single letter to represent my vector. For example, maybe I just want to call this vector V. So V with an arrow on top. If I just want to reference the size or the magnitude of the vector, I'm going to use absolute value signs. For example, the absolute value of V means I want the magnitude of V. And the reason we use absolute value signs is because magnitude is always going to be a positive value, and absolute value signs do just that. In terms of the direction of a vector, we can use different ways to represent it. We can talk about the direction in standard position, where we're talking about the direction with reference to the horizontal. We could use true bearings, where north is 0 degrees and you calculate your angle clockwise from north. Or we could use quadrant bearings, where we use that north-south line and talk about the direction or the number of degrees towards the east or west compared to north or south. And finally, if you are told that there is an angle between two vectors, it is assumed that the vectors are positioned tail to tail. So for example, if I said vectors A and B meet at 40 degrees. Here's vector A, vector B has to have its tail with the tail of A, and it is 40 degrees. This is how the angle representation would be. Next, how can we represent those vectors? Well, we can see a diagram. For example, let's say this vector has a length of 5 kilometers and it's going towards the east. There's my diagram. The arrow shows the direction. I've labeled the magnitude of the vector. If I want to communicate this in words, I would just say 5 kilometers to the east. If I wanted symbols, it's just like I said before, using the endpoints of a vector or just labeling the vector with a letter, whatever you prefer. And finally, you can represent vectors as ordered pairs. For example, if you are in 2D, you can represent a vector with an X and Y. If you are in 3D, X, Y, Z. This notation is specific for algebraic vectors, which will come later on. Next, some important definitions. Some vectors can be equal, and in order for vectors to be equal, they must be parallel. So I'm going to talk about vectors A and B. Vector A is parallel to vector B. This is how we can communicate it nicely. The magnitudes of A and B must be equal in order to be equal vectors. How would I show that with nice notation? The magnitude of vector A equals the magnitude of vector B. And the direction has to be the same. Okay, because remember, just because vectors are parallel, it doesn't mean the directions are the same, because they can be going in opposite directions. So here's a visual example of two equal vectors. Let's say this is vector A. Vector B is equal to vector A if I copy paste the vector. The size is the same, the direction is the same, parallel, and everything. These are equal vectors. And we can say vector A equals vector B. Opposite vectors, very similar to equal vectors, except their directions are opposite to each other. They're still going to be parallel, so now I'll use C. Let's say vector C is parallel to vector D. Their magnitudes will still be equal. The magnitude of vector C is equal to the magnitude of vector D, but their directions will be opposite. For example, let's say this is vector C. Vector D, I'm going to copy paste that vector, but I'm just changing the direction. And a statement I can write here is that vector C is the same as taking vector D and flipping it. So that would be negative D. The negative would imply change the direction of the arrow. And if I change the direction of this arrow going here, that would give us vector negative D, and then they would be equal. So those are opposite vectors. Finally, we can have a zero vector. Its magnitude is 0. Its direction, well, if it doesn't have a magnitude, there is no direction, so it's undefined. And the notation we use is just a 0 with an arrow. That shows that it is a vector, not just a scalar 0. Let's take these definitions and apply them to a few shapes here. I have a parallelogram A, B, D, C. Let's write some examples of equal and opposite vectors. So here's vector AB. Vector AB is equivalent to vector CD. I can also write it the other way around. Vector BA, so that would be going in this direction, is the same as vector DC. Now, I can do the other ones. AC is equal to, going in the same direction, BD, or I can flip-flop it, CA with DB. So the order you put your endpoints in is very important because the first letter would represent the tail, the second, the head. So these are all equal vectors. Let's look at some opposite vectors. So I'm going to go back to vector AB here. It's going in this direction. The opposite vector to AB would be D to C. So if I take DC and flip it, then it'll become the same as AB. So there's my statement. I could also look at A to C is opposite to D to B. They're same magnitude, they're parallel, just opposite direction. So AC equals the opposite of DB. All right, let's go to the next one. We have a rectangular box here. Vector OA is just represented by A. From O to C is B. From O to D is C. Let's express each of these vectors using just A, B, or C. So we're going to start off with GF. Well, that looks exactly like vector A. Same size, same direction. Wonderful. BC. Well, BC is the same length as A, but it's going in the opposite direction. So that's negative vector A. Next we have FB. FB is this. It's the same size as C, just going in the opposite direction. So that's negative vector c. DG is right here, copy paste of b. And finally, FE is this right here. Looks the same as b, but wrong direction. So negative vector b. So looking at your diagrams, reading the directions carefully is very important. Now we can multiply vectors by a scalar quantity. This will change the size of the vector and can potentially change its direction. So for example, if I were to take a vector, let's just say this here is vector A, and let's say I pick a k value, so that's going to be my scalar, that's greater than 0. So let's say 2. I want to draw 2a. Well, I'm just going to take this vector, same direction, that's one of them, and I'm going to double its length. There's vector 2a. And the direction's the exact same, it's just the size is bigger. Okay, so these are not equal vectors anymore. They're still parallel, same direction, but their sizes aren't the same. If k is less than 0, so let's say I could pick negative 2, and it'll be the same size, just the arrow on the other side, but I'm going to pick a different value. So negative a half, let's say, times vector a. So the original vector a is going to be cut in half, so like this, and the direction will change. And there we are. But all three of these vectors are parallel. Okay? And this makes them collinear. So if two or more vectors are parallel, they're collinear. Their magnitudes do not have to be the same. Even their direction doesn't have to be the same. As you can see here, these go in this direction, this goes in the opposite, but they are parallel. And if two vectors are collinear, they can be written with this scalar multiplication. So vector A is equal to a number times vector B. If you can write that, that implies that they're parallel and they have similar directions. Maybe they're opposites, but they are parallel to each other. And it is important that K is not 0. Otherwise, you're creating a 0 vector, which that's not going to be collinear. So if vector A and B are parallel, that's our notation, the magnitude of A is 4, the magnitude of B is 20, show that the two vectors are collinear. The fact that we are told that they're parallel is the reason they're collinear. But I need to be able to express collinear vectors with this type of scalar multiplication. So the first vector A has a magnitude of 4, the second has a magnitude of 20. Well, I can just multiply 4 by 5 to get 20, which means I can take vector A, multiply it by 5, and I get vector B. Now, the only thing that is problematic here is, yes, my vectors are parallel, but it doesn't say if they're going in the same direction or opposite. So this statement can be true, or maybe this statement is true if they're going in opposite directions. So either one can be true here. And another way we could write this, instead of doing 5 times vector A, we could say that vector A is equal to a fifth of vector B. Make vector B smaller. 20 times a fifth will give us 4. Likewise, I can do this. Any 4 of these statements would show that these vectors are collinear. And again, I put a positive and a negative version because just telling me that vectors are parallel doesn't tell me if they're going in the same or opposite directions. Finally, unit vectors. A unit vector has a magnitude of 1, and the notation we use, instead of an arrow on top of the letter, we use this little hat. And that implies that it's vector v with a magnitude of 1. And we can turn any vector into a unit vector using our knowledge of multiplying a number by a reciprocal. If I have a number, let's say 5, and I multiply it by its reciprocal, so the reciprocal of 5, or 5 over 1, is a fifth, that would give me 5 over 5, which is 1. So if I multiply a vector by the reciprocal of its magnitude, I will create a unit vector. So let's look at our final example. The magnitude of vector v is 3. Determine a unit vector that goes in the same direction. Well, if I multiplied 3 by a third, that would give me 1. So here we are. Take vector v, multiply it by a third. That will keep its direction. It'll just change the magnitude to 1. And that's it for various terminology that is very important when dealing with vectors.